Okay, let's pick up from our historical review or introduction to quantum mechanics. In 1926, we have Schrodinger's equation, Schrodinger, as we said. Now, it's a very strange partial differential equation, but we can now recognize at least a few things in it. We see it's negative h bar squared over 2m. Well, we know what h bar is. It's Planck's constant divided by 2 pi. That's h bar. So we have h bar squared over 2m. M is particle mass, the mass of a body. Del squared, so there's our Laplacian operator again. And it operates on this is something completely new to us. Psi is what's called a wave function. So capital psi, and it's a function of both position and time. So r bar is a shorthand notation for the position vector. So here it's a shorthand for position. So this could be x, y, z. It could be spherical coordinates or cylindrical coordinates or whatever coordinates are convenient or that we want to use. That's represented by r. We saw this notation last semester in electromagnetics. So negative h bar squared over 2m del squared psi plus v of r. So this is a function of position only, not of time. We know that the del operator, by the way, is a partial differential operator that operates only on position coordinates or variables. That's not an operator on time. V turns out is the potential energy operator. We'll talk more about operators here in a minute. But it's V as a function of position, and it's multiplied here times our wave function psi. So that's over on the left-hand side. On the right-hand side of the equation, we have I h bar, so I square root of -1. In electrical engineering, we typically use J, but here we're dealing more with physics, so we'll typically often see I. I think our book may actually use J, but it's square root of -1. I h bar partial with respect to t, operating on psi. All right, so there's our Schrodinger's equation. Now we're going to kind of back up. This is where we're going to kind of end. As I said for our historical review of quantum mechanics introduction, that this is kind of a postulate. And this, of course, is on our sheet. It's our first equation on our basic equations for semiconductor device operation. This is Schrodinger's equation. It's sort of a postulate for us, but we can see there's some deeper things that are wrapped up in here. I mentioned that this is, in some sense, a statement of the conservation of energy. So, how does that? Here's a shorthand notation for the Schrodinger equation. H hat, or just H, is the Hamiltonian operator. Hamiltonian operator operating on psi is equal to E hat. This is the total energy operator. So H for Hamiltonian, E for energy, and again operating on psi. What we have in quantum mechanics is that observables, things, quantities, that is, like energy, position, momentum, they have associated with them operators. And these operators, they're not variables, they're not functions, but, well, they can be functions, but they're not necessarily functions. And they have these operators associated with them. Rather than variables. Now, we'll eventually see that we can get values of energy and position and momentum and things like that, those that are observable. But at a basic level, these observables, instead of having variables like P, X, E that are directly associated with them that you can measure, they have operators. Instead, they have operators. And we're going to denote operators with a hat. If we have just kind of a generic operator to make sure that we are clear that it's not a variable or a function, we're going to denote it with a caret or a hat to indicate that it is that it's an operator. And the operators, and we operate on the wave function, psi. So we have psi as a function of position and time. We see that this operator is operating on psi, whatever this operator is. This is an operator, it operates on psi. This is an operator, it operates on psi. Well, you can also look ahead and think, oh, well, all of this is probably H, the Hamiltonian. That's true. And this I, H bar, partial with respect to T, is the total energy operator E hat, and that's true too. But we're gonna kind of go a little bit further still and see kind of what this means. All right, so operators. Some important operators, some especially maybe important operators in quantum mechanics. First, we have the linear momentum operators. The x component of the linear momentum has as its operator negative I h bar partial with respect to x. Similarly, the y component of the linear momentum, its operator is I h bar partial with respect to y, and the z component of the linear momentum operator is negative I h bar partial with respect to z. Now these would then have a unit vector associated with them. We could use x hat like we did x hat, y hat, and z hat to give the direction for these as we did last semester in electromagnetics. Or we could use I hat, j hat, k hat, more commonly used in mathematics and physics. And so that's actually we'll use that here. So the total linear momentum operator, and including the vector component, the direction, is negative I h bar delta. Delta, our del operator. And you recall that in Cartesian coordinates, the del operator is I hat partial with respect to x plus j hat partial with respect to y plus k hat partial with respect to z. So you can see that clearly these would be the components of our linear momentum operator. All right, so these are important operators in quantum mechanics. What are some others? Well, the position operator, R hat. Now here, hat means operator. Unfortunately, we're kind of using the caret for both operator and unit vector. But here it's an operator. The position operator is equal to the position vector. Now, this operator, which we don't actually see up here in Schrodinger's equation, but we can make use of it, it will operate on psi, and it's a multiplicative operator. So when we put psi to the right of it, it will simply multiply times psi. Clearly, we saw with the momentum operator, linear momentum operators, they're partial derivatives, and they operate on psi. They'll take the partial derivative of psi with respect to x, y, or z, or whatever. All right, so we got a position operator. Now, the kinetic energy operator, T hat, well, it's our linear momentum operator squared over 2m, or the linear operator dotted with itself, really. It's what we can, but this looks just like E equals p squared over 2m, which from classical physics, p squared over 2m, which we've been using. But here these are operators. So what this means, in greater detail, we know the p is negative I h bar del, so we dot that with itself, and we have negatives cancel, but then we have an I squared, so we still have a negative. We have h bar, so we have h bar squared, and we have del squared, or Laplacian, over 2m. Okay, so kinetic energy. Well, there's our kinetic energy operator that we see in Schrodinger's equation. So we have kinetic energy operator, which shows up in our Schrodinger equation. The potential energy operator. V. So thinking as an operator, we have V hat. This is simply the potential energy as a function of position. And we see it right here. It is also like the position operator, it is multiplicative. So we put psi over here, it simply multiplies times psi, and that gives us our potential energy. Now, as I mentioned, so the Hamiltonian operator is then pretty clearly the kinetic energy operator plus the potential energy operator. So here again, our Hamiltonian represents kinetic energy plus potential energy. And that should be equal to total energy. And in fact, the total energy operator is what we have on the right of our Schrodinger's equation, is I h bar partial with respect to t. That is our total energy operator. So that's what I called earlier E hat. E hat I h bar partial with respect to t. So this gives us h hat operating on psi equal to E hat operating on psi, which means we have kinetic energy plus potential energy equals total energy. So there we have our conservation of energy. This is then also known as, this Schrodinger's equation, kind of the whole shebang, is the time-dependent Schrodinger equation. So we have the time-dependent Schrodinger equation. We can also see that